All right, so we're going to finish the semester by talking about altitude. I hope everybody had a good Thanksgiving. It's super fun to be up at work at 11 o'clock in the morning, day after Thanksgiving. Sorry for getting this out a little later than I would like. Just some stuff keeps popping up with other work-related stuff. So anyway, here goes nothing. So we're going to talk about acute and we're going to talk about chronic. So there's only 2 videos here that you'll need for altitude. So remember, acute is just short-term exposure. How does that affect things? And then chronic is you've been there for a long time. So here are the objectives. And we're really going to focus on aerobic activity just because, well, anaerobic means without oxygen. And so if we go from lots of oxygen to not so much oxygen, but the activity doesn't require oxygen, it's not going to have a big effect. So remember, this is important to know, is that altitude specifically doesn't have any effect on your physiology. Okay, so just the act of going up higher in the atmosphere doesn't do anything. But what happens is as we go up in altitude, we have lower barometric pressure, which means there's less oxygen. Therefore, we have lower pressure, right? And we call this hypobaria. And so the changes in the pressure alter the amount of oxygen that's in the atmosphere and then therefore the amount of oxygen that gets into your body. So if you remember from our cardiovascular section and the oxygen cascade, we talked about how the amount of oxygen in your inspired air is about 150. By the time it reaches your alveoli, it's down to about 100, 105. And then because there is an AaDO2, it's about 100 by the time it gets into your blood. Okay, so this is what we've already talked about over here. Well, notice, though, if we go up high in altitude, and this is about 15,000 feet. So this is top of the Rockies, actually probably a little bit higher. The amount of oxygen in the air is almost reduced by 50, and then it's still displaced by carbon dioxide. So we go from 83 to 47. We have the AaDO2 there. It's actually a little bit larger at altitude. And so by the time we get stuff to your arteries, or in our arteries, we're at 42. And notice that that's just barely above what you normally have in your venous blood. Okay, so let's take this back to the oxyhemoglobin dissociation curve. All right, so in our alveoli, I want you to remember this, in our alveoli at around 7,300 meters, which is really high, right? So this is 23,000 feet. We're at this part of the curve, okay? When we're about 15,000 feet, we're right here. You know, I know that I've got an arrow, but that's right at the shoulder of the curve. And so that's where things start to get a little dicey, where your body's like, this isn't great. But normally we're up here, mid 90s, high 90s, okay? And so we're on this flat part of the curve. We've got a lot of room to, basically a big buffer that we can lose a lot of oxygen and it's not a big deal. But once we start getting down towards the shoulder, then that can cause some problems. And so when we're at altitude, really all it comes down to is that there's less oxygen. And so since there's less oxygen in the blood, we deliver less oxygen. That's the big thing. Okay? And so as a result, aerobic performance is affected. All right? And it has what we would call a dose-dependent response, meaning the higher the altitude or the less oxygen, the bigger the effect. Okay? And for the most part, it only affects endurance performance. Okay? And so we're talking about things that take more than 2 minutes or so. Because before that time, our anaerobic systems can cover the cost. All right. Now, if you remember from PE 220, we've got chemoreceptors in both the brain and near the heart. And so these peripheral chemoreceptors, or the carotid bodies, which are located right in the aortic arch, right in their carotid sinus, they are the ones whose job is to primarily monitor pressure of oxygen. And so when that pressure of oxygen gets below 100, there is a stimulus to increase, but really we've got to get much lower than 100 for us to have a significant ventilatory response. And so this results in hyperventilation. We're actually, what happens is we're breathing more than what we need. And you're like, well, wait, we have low oxygen. Well, remember, hyperventilation is tied to carbon dioxide. Okay, and so just being in altitude doesn't necessarily change our metabolic demand, or we're not producing more CO2 just because we're at altitude, but as a result, we breathe more. Okay, and this is the biggest response to altitude. And why? Well, the big thing is that this hyperventilation increases alveolar oxygen. Okay, and so normally, if you look at this figure, let's just say normally we're at about 4.2 liters of oxygen or liters of air per minute to our alveoli. Well, if we hyperventilate, notice our arterial oxygen goes up. If we hypoventilate, it starts to go down, right? This isn't anything new. And so that primary response is hyperventilation stimulated by peripheral chemoreceptors. Ultimately, what this is doing is it's increasing alveolar ventilation. We've talked several times how we'll actually increase the size of our breaths. And so by doing that, that's going to also help to increase our alveolar ventilation, ultimately resulting in a higher alveolar oxygen, which means we have a bigger gradient, which means it's easier for oxygen to get into the bloodstream. Okay, and so as a result, this hyperventilation also increases saturation. That's what this curve is showing us, the relationship between pressure and saturation. Okay, and so if we have high pressure in alveoli, we'll have higher pressure in the pulmonary capillaries, high pressure of oxygen. I'm not talking about the actual blood pressure. Okay, this lowers CO2, it increases pH, or it also lowers acidity, and so that actually causes a left shift, and that's what we're trying to see here with this figure. And so it makes it easier for oxygen to bind to hemoglobin, and so when we're in a situation where there's low oxygen, this is a good thing. Okay. However, most likely your arterial blood will still have a lower saturation and a lower pressure relative to sea level. Obviously, this is dependent on what altitude you're at and how big your response is. But generally speaking, you're going to be lower than what you are when you're here in Terre Haute. Okay, so let's look to see how this affects, how hypoxia affects performance. Now, first of all, let's go back to how our cardiac output changes with training, right? So on the x-axis, we've got intensity. On the y-axis, we've got output. Now, these lines should be right on top of each other, but if they're right on top of each other, it's hard to see. Okay, so just for every intensity, just notice that just assume that cardiac output's essentially the same. However, before we're training, due to a decrease in stroke volume, we hit our max cardiac output here. Okay, we can go a little bit longer, obviously, because of the anaerobic systems. But after training, we'll have some adaptations, some cardiovascular adaptations, and so our stroke volume will increase, which means our max cardiac output increases, and so we can go for a longer period of time, and really this should probably be extended out even more. Okay? Now, with altitude, it's a little bit different, obviously. Okay? Now, notice here that before training, we keep that same line, right? All right, but at altitude, for a given intensity, cardiac output is increased. So why is this? Why do you think the cardiac output increases when we're at altitude? Well, the answer is there's less oxygen, and so in order to deliver the same amount of oxygen, my heart has to work harder. And so for a given intensity, at altitude, cardiac output will be higher. But what happens is we hit our max cardiac output earlier, and so we're not able to work as hard. Okay, so just to see this in words, at submax activity, cardiac output will be higher at altitude than it will be at sea level due to the increased heart rate. Okay, altitude doesn't change max heart rate, but it does happen at an earlier or a lower intensity, and so as a result, you have a reduced VO2 max at altitude. Okay, and that's not to say you couldn't use more oxygen, but your heart just can't work hard enough to deliver enough oxygen. Okay, so the last thing that I want to show you here is this crazy figure. Okay, and this is this was from a paper, and the weird thing is you get this off the website that the paper's published on, and the colors don't line up. So I'm trying to show you that, where the different lines match. Okay. And so I really want you to just focus on the acute side of things here. Okay, so we're going to kind of cut this right here. All right, so really there's three lines that we're focusing on. Okay, so we've got this little green one here, which is ventilation. Okay, we've got this kind of lime one, which is something called HIF1 alpha that we won't really talk about. I'll mention it here in just a second. And then we've got this black line, which is appropriately labeled, which is cerebral blood flow. Okay, so I want you to notice that we have the time scale of minutes here. So what happens when we first are exposed to altitude? Okay, the answer is we have a spike in ventilation. Our ventilation might increases quite a bit. Okay, we almost experience the highest level of increased ventilation in the first 5 or 10 minutes. Okay, we call this the hypoxic ventilatory response. Notice, though, that at the same time, cerebral blood flow actually decreases. Okay, and this is because we're getting rid of so much CO2, the brain goes, oh, I don't need as much blood. All right, and then gradually that increases. All right, and then this HIF1 alpha, this is an enzyme protein that actually signals the production of more red blood cells. Okay, and so the longer that we're in altitude, the greater the stimulus for this HIF1 alpha becomes. All right, so initially our big response is this ventilation, which causes an increase in oxygen, a decrease in CO2, and that decrease in CO2 also leads to a decrease in blood flow. Okay, and so we can look at it from this figure here, kind of the same type of thing. Now notice we've got a lot going on here. So we've got saturation, we've got alveolar oxygen, and we've got ventilation here. And notice, and so for saturation, it's got its own line, and for arterial oxygen, it's got its own line, right? So we got here and we've got here. Okay, so notice that as saturation increases, ventilation decreases. And the same is true of arterial oxygen or alveolar oxygen as well. Okay, and we can take the information off this figure here, off the left side, and then we can look at what's going on in the right side. Okay, so again, we're going to focus just on the left side of this figure. Okay, this is the acute response here. A is for acute, C is for chronic. We're just worried about the acute. So notice during the first 10-15 minutes, we have a big spike in ventilation. We almost increase by, we almost double. As a result, our CO2 drops pretty significantly, and our arterial oxygen drops a little bit because we're not only are we breathing more, but we're trying to compensate for the fact that we're at altitude. So you're like, well, why is this dropping? And the answer is because we're at altitude. Okay, and so this study that this is from is basically like, just say we were in the lab, and then we had you breathe on a mouthpiece that had just low oxygen. Okay, so the last thing here is that the spike in ventilation really kind of decreases after 30 minutes. We aren't completely sure why. We think it has something to do with the fact that we've got low CO2. Because remember, you've got two drives to breathe. You've got low oxygen and high CO2. Well, if you've got low oxygen, that actually causes you to breathe more, which causes your CO2 to go down, and then you're losing that drive to breathe from CO2.